Okay, welcome back everybody. We're going to continue our knowledge on limits now that we know exactly what a limit is, and we're going to start evaluating some limits. So, this top one we have here, this is very similar to the limit that we did last video. This second limit is a very interesting one. We see the root, but we'll get to that. Very interesting theory that we'll use there. I guess not really a theory, but just a strategy. Now this is our interesting theory limit that we will see at the end of the video, where I will get into a bit of the theory. But we could also use it another way, but I like to do the fun stuff sometimes. So this one, pretty easy. We just have x squared minus 4 over x minus 2. Now you'll notice x squared minus 4 is a difference of squares. So what's this equal? Well, it equals the limit as x approaches 2, of course. But we're going to split up this x squared minus 4 into x minus 2 times x plus 2 over x minus 2. And so what's that equal now? Well, that just equals the limit as x approaches 2, and we'll cancel these two out, of x plus 2. And now we notice x plus 2 is defined at x equals 2. And what's that equal to? Well, 2 plus 2, which is quite an easy task. That's just 4. So, those ones are pretty simple. A lot of the times when you see something that can be factored on the top or the bottom, or both, a lot of the times we want to do that just to cancel out that factor that, you know, makes the bottom equal 0 or whatever it be. So, next one is the limit as x approaches 0 of root x minus 1, or plus 1, sorry, minus 1 on the outside over x. Now, a lot of the time when you see a root, you kind of want to get rid of it because they're just annoying. So that's what we're going to do. We're just going to take this and we're going to multiply by the conjugate of the top. This is something that we're going to use a lot, multiplying by the conjugate in limits. It's a very useful strategy. So we're just going to take root x plus 1 plus 1 over root x plus 1 plus 1. And we know this just equals 1, so it equals the same thing. So this is going to give us the limit as x approaches 0 of, well, we've got x plus 1, both rooted, times each other. We're just going to get x plus 1. Put that in a bracket for now. And then we've got, well, this is very similar to what we did up here, isn't it? It's almost like a reverse. We've got a difference of squares, so that's just going to be x plus 1 minus 1 over x times root x plus 1 plus 1. And so what happens up here is this 1 and this negative 1 are going to cancel, and we're left with this. We're left with the limit as x approaches 0 of, I'm going to do it right at the bottom first. A little jammed. This one over x. And now we notice we have a common factor on the top and the bottom, just like we did up here. And what we get is the limit as x approaches 0 for just 1 over root x plus 1 plus 1. If we let x equal 0, we've just got 1 over root 1 plus 1, which is just 1 over 2. Not too bad. Well, let's get into this fun one now. Now for this, we're going to have to use what we call the squeeze theorem, or the sandwich theorem, they might call it sometimes. That's what my high school teacher called it. My university professor called it the squeeze theorem. Totally up to you what you want to call it. But all this says is that if we have three functions, and I know that sounds a little confusing here. Three functions, where are we getting three functions from? But we'll get to that. And we'll choose A, again, as we did in the last video, as our point where we want to evaluate the limit. And let's say that for all of these functions, the top function is always greater than the middle function, which is always greater than the bottom function. Then, if the limit as the top function approaches A, and the limit as the bottom function approaches A, well, if the middle function has to be in the middle of them, then what's the middle limit got to be? It's got to be A, because it's being squeezed through, or it's being sandwiched in there. Squeeze or sandwich theorem. So, strange, right? But, what if we think, well, sine x, we know what sine x looks like. Sine x, that's our middle function, because we want to find the limit of that. So we're putting it right in the middle of these greater than or less than and equal signs. So sine x is always greater than or equal to, well, what's -1? Sine x is always less than 1. We know that because sine of x just goes like this. And this would be 1, and this would be -1. Easy stuff. So, how are we going to make this function this function? Well, that's easy. We'll just times it by x squared. So if we take -x squared, it's less than or equal to x squared sine x is less than or equal to x squared. That's an interesting little notation we have here, or whatever you want to call it. But what we'll notice here is if I redraw this again, no, there's a lot of drawing here, but we don't actually, I just want you guys to visualize this. Is if I draw -x squared, we're going to get this. And I get positive x squared, we're going to get this. And what's our a value? Our a value is 0. X is approaching 0. And at 0, the limit for both of those functions equals 0. So that's going to tell us that the limit as x squared sine x approaches 0 is 0. That's because if we actually draw sine x, or x squared sine x, sorry, we're just going to get this. Because this is just the amplitude. Our amplitude is x squared. We remember that from graphing trig functions in pre-calculus. And so what we're going to get is, if we take the limit as x approaches 0 on both sides, we're going to get limit as x approaches 0, -x squared is less than or equal to, the limit as x approaches 0, x squared sine x is less than or equal to the limit as x approaches 0 for x squared. So, the limit as x approaches 0 for x squared sine x, it's got to be greater than what this is. Well, that's just 0. We can see that from our graph, or we can see that just from plugging it in. This is also going to be 0. So, if it's less than or equal to 0, and greater than or equal to 0, it's just got to be 0. So that tells us the limit as x approaches 0 for x squared sine x equals 0. Boom. That is the squeeze or sandwich theorem. That's how we're going to evaluate most of our limits. Not that, but one of these three tricks, and well, we'll learn one more when we learn derivatives, which we're going to get into very soon. I just need to show you guys limits that equal infinity, limits at infinity, and they're pretty easy stuff. So, yeah, thank you.